When it comes to human scent, volatile sulfur compounds and organic amines are the primary chemical architects of halitosis and body odor. The standard industry response to these compounds is the superficial masking technique, creating a barrier of pleasant scent around the target molecules. The structural flaw here is volatility. Because synthetic fragrances are designed to be noticed, they flash off the application site quickly, leaving the stable, malodorous sulfur and amine structures behind. In many cases, the residual chemical remnants of these masking agents can interact with the environment to increase the volatility of the original odor molecules. This rapid evaporation of top notes suggests that long-term efficacy depends on a mechanism that dismantles the odorant at the molecular level. Zley Orafine is engineered for this specific purpose, operating at the intersection of targeted botanical extraction and structural chemistry. The objective is the physical and chemical modification of the environment to a state where malodorous compounds are incapable of persisting. The first pillar of this multidimensional approach is chemical decomposition. The primary active agent is a natural, food-grade bamboo vinegar extract. Upon contact with hydrogen sulfide, the vinegar's conjugated double bond systems initiate immediate catalytic redox reactions. This reaction triggers the physical cleavage of the compound, rearranging the sulfur molecule into odorless elements like water and carbon dioxide. This technical schematic from the Zley documentation illustrates this pathway, demonstrating a breakdown of these gases without generating secondary pollution. This reaction matrix is concurrently calibrated to target volatile organic amines, the compounds responsible for ammoniacal odors. To address these amines, the formula utilizes Rosa damascena flower water. Specific organic acids derived from the Damascus rose initiate rapid acid-base reactions, neutralizing the amines immediately. Through these dual reactions, offensive gases are chemically dismantled before they reach human olfactory receptors. The second pillar relies on physical adsorption, utilizing a mechanism known in supramolecular chemistry as host-guest interaction. Hydroxypropyl cyclodextrin functions entirely through its three-dimensional ring architecture, featuring a hydrophilic exterior and a hydrophobic inner cavity. This structure is engineered to target short-chain fatty acids, such as isovaleric acid, which are the primary causes of lingering body odors. The fatty acid molecule acts as the guest, which is drawn into the hydrophobic cavity of the cyclodextrin host. Once inside, the physical dimensions of the cyclodextrin barrel hold the fatty acid in place, keeping it permanently sequestered. While volatile masking agents eventually release trapped odors as they evaporate, this physical microtrap removes the odorant from the sensory environment entirely. Engineering a physical microtrap allows formulators to eliminate heavy organic odors without introducing harsh reactive synthetic chemicals into a product matrix. The final pillar focuses on biological modulation to address the root microecological causes of odor generation. Traditional hygiene products often rely on broad-spectrum biocides, which can lead to total sterilization of the application site. Complete sterilization creates a biological vacuum, inviting oral flora dysbiosis and the rapid rebound of malodorous pathogens. The Zley matrix replaces total sterilization with selective microecological balancing, specifically targeting the pathogens that generate volatile sulfur compounds. This clinical data table tracks the formula's efficacy against Streptococcus mutans, a primary pathogen driving halitosis. Under the WST 650-2019 standard evaluation, a 3% dilution achieves a 99.61% bacteriostatic rate within 5 minutes. Suppressing this specific pathogen reproduction stops the continuous generation of new sulfur compounds at the source. This targeted bacteriostasis allows formulators to halt odor production while preserving the natural microecology of the human host. In cosmetic chemistry, high active potency is typically accompanied by severe formulation constraints or stability issues. This technical datasheet outlines the INC matrix of Zley Orafine, demonstrating a stable, water-soluble profile. The core active drivers consist of bamboo vinegar at 15 to 20%, Rosa damascena at 14 to 20%, and cyclodextrin at 5 to 10%. This efficacy is achieved with a strict zero stimulation profile, 0% alcohol, 0% synthetic essence, and 0% traditional harsh preservatives. The supporting stability matrix utilizes highly tolerated compounds like 1,2-hexadiol and hydroxyacetonephone at less than 1% total concentration. For formulators, the application parameters are direct. Optimal efficacy is achieved at a 2 to 10% dosage, and it disperses easily at room temperature. The entire matrix is environmentally compatible and inherently biodegradable, preventing secondary aquatic pollution upon disposal. This specific component profile indicates that formulators can maintain a clean label mandate while achieving clinical-grade deodorizing performance. In modern cosmetic development, traditional reliance on high-concentration masking fragrances is being replaced by targeted molecular engineering. High-efficacy deodorization treats the microenvironment as a holistic system. This involves breaking down volatile sulfur compounds chemically, trapping fatty acids physically, and balancing the oral flora biologically. This complete molecular dismantling provides a level of stability that the temporary, volatile masking technique cannot replicate. Utilizing the Zley Orafine matrix allows formulators to return the microenvironment to a neutral state, preventing the recurrence of the biological trigger. Formulators must evaluate if their products are providing a long-term solution, or if they are simply layering one volatile compound over another.